Hi everybody, it's time for the last video in lecture module 3. This is video 4, where we will be talking about a rather important topic, climate change, specifically anthropogenic climate change or climate change driven by the human production of CO2, the insertion of an increased number of greenhouse gases into the atmosphere. I know this is a weighty topic, it can be pretty controversial. I am going to bring a scientific approach to this, so don't worry, this is not going to be a political video in any way whatsoever. So I've brought up my slides. So we are going to talk about anthropogenic climate change, or really just climate change in general, and I'm going to talk about how we have linked human production of CO2 through the burning of fossil fuels to the temperature changes we have seen over the past few decades. So I want to be very clear about this. I am going to take a scientific approach, not a political approach. I am not a climate scientist. I have done a good bit of climate studies, and I've taken several classes in climate science, mostly focused on how atmospheres behave, including some general circulation models that are akin to the climate models that are used. At one point in my life, my PhD work involved atmospheric modeling of Mars. So I was modeling Mars's atmosphere. And I did spend some time at the University of Oxford. The department I was in was the atmospheric, oceanic, and planetary physics subdepartment of the physics department. So I did get to see weekly talks from some of the leading climate physicists out there in the world every week. But by no means am I a climate scientist, but I do probably know more than the average person. So I'm going to share you my perspective of the science and also related to concepts we've heard in class and we covered in the last video. We'll start with historic measurements of CO2, so we can see that there has been a spike of CO2 in our atmosphere, and then we will link that to human-produced CO2 through the burning of fossil fuels. We'll have to rely on our knowledge of isotopes to do that. There is a very clear isotopic fingerprint that it is all the increase in CO2 is not from natural factors, it's from humans burning fossil fuels. Then we'll actually talk a little bit about the climate models, how they work. One of the key factors or key principles of those are these things called forcing factors. And we'll discuss about the climate models just in general, what kind of predictions they have they fulfilled predictions, how they work, things like that. Just for another point of clarity, a lot of this video is just for your edification. It's really hard to test the deep concepts on this. So other than just the generalities, a lot of this material is for your edification. There, of course, will be some questions to make sure that you're absorbing the material. But all the fine detail is a little bit beyond the scope of this course. If you have any questions about what will and will not be, go see the quiz hints, exam must knows, things like that. Or ask me, send me an email. Okay, let's start with the basics. If we're going to talk about climate change and climate science, we should go ahead and take care of a common misconception that people usually don't have, except whenever they're making decisions in the moment, or sometimes they are just broad misunderstandings between the two different terms, climate and weather. Two separate things. Let's start with weather and then we'll go to climate. So weather, our short timescale day-to-day phenomenon, is what's happening with our atmosphere in our local area right now on a day-to-day, week-to-week basis. So these are short timescale phenomenon. These are things like if we look outside, I'm not sure if you'll be able to see out my windows or not, but we're kind of a cloudy day. It might rain a little bit. So it's been a very rainy spring around here. Most days have been rainy. Rain is a weather effect. If it's hailing, just like it was on those crazy storms we had very recently, well, that's a weather effect. A tornado is a weather effect. A hot spell, like today is cool, tomorrow will be hot, that's a weather effect. So these day-to-day predictions, what you listen to a meteorologist for, they're trying to predict the weather. These short timescale effects are harder to predict. What's a lot easier to do is to observe weather over a very long time scale, months to years to decades. And then you can characterize that with statistics and get sort of what the normal state is for a region or the globe. So if you're talking about a long time scale characterization of a location, you're talking about climate. So it's sort of a time average of weather of a region. It characterizes the norms of an environment. Saying that East Tennessee is a temperate deciduous forest is a climatic thing. Saying that southern New Mexico is a desert is a climate statement. Saying that the East Coast experiences hurricanes and has a hurricane season, that is a climate statement. Saying that this area is a rainforest is a climate statement. Heck, even saying something like the average March, well, I guess it should be April now, high and low temperatures for East Tennessee are 61 degrees Fahrenheit as a high, 40 degrees Fahrenheit as a low is a climate statement. Saying what the average temperature in Tennessee is a climate statement. Saying what the average temperature of the globe is a climate statement. Saying what the average temperature of the northern hemisphere, the southern hemisphere, every continent, that's all climate. Things like average rainfall, annual rainfall, is a climate statement as well. So climate, long time scale, weather, short time scale. Climate, since it's a long time scale averaging, we can bring to bear statistics, which means that we have good predictive power. Weather is short time scale, highly variable, hard to actually get good predictions, a higher level of uncertainty from day to day. So what is climate change then? Well, a climate change is we have these well-characterized norms that are characterized over a long time scale, and when that norm is changing. So that could be globally, it could be regionally, and this includes changes in the average temperature of a region like the southeast of the United States, the entire North American continent, or the globe. So it could be changes in temperature, rainfall, wind speeds, when winds are, how strong winds are, average number of sunny and cloudy days, things like that. So anytime that we see these climatic norms changing, that is climate change. And we are observing a climate change. And the climate has always been changing. That is a fact. This just everything is following all of these trends. What we are concerned about is that the current change that we are seeing is rapid beyond timescales we've ever historically observed and that we've observed over any timescales. And we are trying to understand what the current climate change is, what the factors are, how strong is the effect, and what is the cause of the effect. So that is anthropogenic climate change, the human-induced part. So let's focus on that. And we have a big concern. Human activity, since the Industrial Revolution, where we've been using fossil fuels on the reg, is measurably increasing the amount of CO2 that we are putting into our atmosphere. You can't burn a bunch of hydrocarbons, which whenever you burn them, they release CO2, and not expect that CO2 to go into the atmosphere. So as we burn large volumes of fossil fuels, we are pumping CO2 in the atmosphere, and we can actually measure an increase quite easily by seeing that there has been an increase over time. So we see that there is an increase of CO2 in the atmosphere. Remember, CO2 is one of our greenhouse gases. It's one of those gases that very easily absorbs infrared radiation. So we have the sunlight heats the Earth's surface up. Earth then re-radiates as a black body, sends infrared radiation trying to go back to space, and any greenhouse molecule can absorb that outgoing infrared radiation, and then whenever it re-emits it, it has 50% chance of going down, 50% chance of going up. We put more greenhouse gases in the atmosphere, it's going to capture more of the outgoing heat, outgoing thermal radiation, and send it back down to the surface. It will increase the greenhouse effect past the plus 33 Kelvin that we have right now. Our question is, how much is it going to change it? How is that going to play out when we consider not only our atmosphere, but the ground, the oceans, and everything else? So the fact that we're putting more greenhouse gases in the atmosphere is changing the strength of the greenhouse effect. In general, more greenhouse gases means that you're going to have more energy going into the surface, which is going to increase the temperature of the oceans and the atmosphere. Just a little bit of extra information that I have here in green. So we also have to consider not only just the atmosphere, but where the the extra energy is going, what layer is it going? We saw the stratosphere is hot because ozone absorbs there, so we need to consider where the energy is being deposited and where we're actually measuring our temperatures from. So you'll see a lot of people that argue against climate change saying that the temperature record can't be trusted because scientists corrected and adjusted it and they made it fit the data. No, that's not what these corrections were. Every instrument measures at a different altitude. Some of them are sensitive for measuring stratospheric temperatures, upper tropospheric temperatures, mid-troposphere, lower troposphere, surface temperatures. So if we want to use all the temperature data we have available to us, then we need to actually use a little bit of understanding of our own atmosphere to normalize the temperatures to all be measured at the same level in the atmosphere. So whenever you see people saying that the corrections were basically scientists just monkeyed with the data to make it fit, no, we adjusted the data according to physics and science so that we're measuring and comparing apples to apples. And when we made that, we were actually even more concerned because it made the situation look a lot worse. We did not fit the data. We did not change the data to fit a predetermined cause. What we really want to know is what consequences does increasing the greenhouse effect have? How will that change our climate, both globally and regionally? So let's look at some of the consequences of increasing a greenhouse effect so we can understand the nature of the problem. So if we increase the greenhouse effect, this is what will happen. We increase the number of greenhouse gases, CO2. That's going to increase the greenhouse effect, which will make temperatures rise. That's how this entire greenhouse effect works. And yes, that's going to be temperatures. You have to consider both the atmosphere and the oceans. And I've said that a lot now. One of the things to keep in mind is that oceans are made out of water, which have a high heat capacitance. You can dump a lot of energy into them, and they'll only change their temperature a little bit. But you've stored that energy. So seeing a very small change in oceanic temperatures is very, very worrying, and we are seeing that as well. So you have to consider both of these things. The atmosphere interact and exchange temperature via energy, things like that, or energy via temperature. So this will change our climate in a variety of ways. One of the main predictions is an increase in temperatures. So atmospheres and ocean. With increased temperatures, we'll have an increased melting of sea and land ice. This is pretty easy to see. I have some information in the supplemental slides about the melting of sea and land ice. And then as land ice melts, you're putting more water into the ocean, sea levels will rise. But also as we increase the temperature of the oceans, as you warm things up, they expand. We have the thermal expansion, which is actually one of the main drivers of sea level rise right now, is the increased temperature. If you put more energy into a system, then you're going to have more energy going into this convection, and you're putting more energy into our troposphere. So that means that you're going to fundamentally change all these weather patterns that we see. So we will change wind patterns, our trade winds, our jet stream, our polar vortices, and things like that. We will change our ocean currents. Also, with more energy, we're going to have a larger variation in weather phenomenon. We're going to have hotter hots and colder colds. We should, and we're now seeing an increased measure in the strength of storms, not only hurricanes, but storms in general. We'll see larger variation and larger fluctuation, more frequent floods and more frequent droughts. So the extremes get more extremey. So again, we're trying to see, like, knowing the basic physics of how greenhouse gases work and that we are putting more greenhouse gases in the atmosphere, we want to see how strongly will it affect the climate. How worried should we be? Should we be concerned? What kind of things can we expect based on the science? So the answer is converging, that we should all be quite concerned. I'm not going to go into the political things, but from a scientific standpoint, looking at the ramifications of these and how those will play out, this is a serious concern, and we are already acting a little too late. But let's look at some of the data. So here we have the historic record of CO2 concentrations in the atmosphere. So this is going back all the way to 800,000 years ago. And then the y-axis here is the amount of carbon dioxide in parts per million. So you can see you have normal fluctuations. A lot of these are driven by things like the Milankovitch cycles, which are astronomical cycles. If you want more information, I have some in the supplemental slides. They are part of the drivers of the glacial and interglacial, or the glacial and interglacial phases. So we have this variation, and how do we know this variation? This data that goes way back comes from ice core data. One of the main ones is the Vostok ice core, where you drill down into ice, say in Antarctica or some other location where the ice is kilometers thick, and then you pull out an ice core. There are little bubbles of trapped atmosphere in there. You extract that atmosphere, you measure the CO2. We have a number of ways of verifying what depth equals roughly what age back, so we can reconstruct a historic record. And then, of course, we have modern record keeping, and what we're really concerned with is here's the normal timescales of variation and the amount of CO2, and here's the Industrial Revolution, and boom. This is sometimes called the hockey stick, that we have skyrocketed past anything that we've ever really seen in the past about million years or so. So we are now currently over 400 parts per million. If you want to put that in parts per 100, i.e. percentage, that is 0.04% what I was giving about atmospheric composition. So yes, there is a larger amount of CO2 in our atmosphere. We can measure that. How do we know that it's actually from fossil fuels? What is the fingerprint that goes, aha, yes, that is from fossil fuels rather than from some other natural factor? And this comes down to a pretty nuanced concept. So you don't need to remember any of this for quizzes or exams. But the CO2 that's generated by burning fossil fuels, by burning what used to be life that has now changed into a fossil fuel, that leaves a very, very, very distinct carbon and, well, mostly a carbon isotope ratio. So this is what we call fractionation of isotopes, and biology will fractionate carbon and oxygen isotopes different than how geologic processes will. Let's pay attention to the carbon one. So over here, I have information about the 3 carbon isotopes that are in play, carbon 14, 13, 12. This is about 1 in 1,000 carbon atoms. This is most carbon. This is about 1 in a trillion carbon atoms. And biological life will preferentially uptake the lighter isotopes, the lower number isotopes, than geologic processes will. So that'll give it a distinct carbon ratio. So then if we wait for that life to turn into a fossil fuel, it'll still have the same isotopic ratio. Then we burn it, change that carbon into CO2, and put it into the atmosphere. Then what we would expect as we burn fossil fuels is we would expect that the isotopic ratio of carbon, the lighter carbons, the heavier carbons, would go up, or the isotopic ratio of heavier carbons would go down. And that's exactly what we're seeing. See that these are bigger negative numbers. So we can go ahead and build models on what we would expect based on the amount of CO2 we're putting in and how the isotopic ratio should be changing. That's our fingerprint. Then we can compare it to the actual data that we measure, and it's a dead match. So this is called the Seuss effect, not Dr. Seuss, although he was a doctor, but not that Dr. Seuss. And that's, we can measure the isotopic ratios in CO2, mostly the carbon ratios. And that gives us a match that confirms that this is human produced by burning fossil fuels. So yes, CO2 is increasing, and yes, it's from humans burning fossil fuels. CO2 is a greenhouse gas. So how do we actually go about incorporating this? How do we actually build our models? How do we interpret this in a scientific way that comes back down to this energy balance that we talked about with the greenhouse effect? So remember that we had the solar constant. This is how much energy the surface solar energy is hitting the top of Earth's atmosphere. This is how much energy is, this dictates how much energy is going in. Whenever we talk about this in climate science and climate physics, we call the solar constant the solar forcing. That's the total amount of energy going in. This is how we build our energy budget, and we got to balance our energy budget to figure out where energy is and how it's changing. So this is what normal is, and then we have to take into various factors, natural factors, and the one that we're going to be paying attention to is factors from greenhouse gases. We call these forcing factors. And really what it is a forcing factor is just telling you how much you're changing, how many watts per meter squared are you changing the solar constant. The solar constant remains the same, but how much are you changing the energy in? So how much are you adding to it or subtracting from it, because there are positive and negative forcing factors. And we can track each and every one of these with the forcing factors. It's things that we track. Again, see supplemental information for more of it. The solar energy output, so the actual change in the solar forcing factor due to solar cycles. We can track that. We can do land use changes like deforestation, changing the Earth's albedo and things like that. We can do aerosol production from urbans. That's a negative effect. That's a cooling effect. So that's a negative forcing factor. We can do aerosols from volcanic venting. That's a natural forcing factor. We can do forcing factor from volcanic CO2. That's a very small forcing factor. And then we can do the forcing factor due to CO2 created by burning fossil fuels. And that's this factor right here, the largely overwhelming factor. So that's just running some physics on how much we're changing the energy balance. We can go ahead and do that. You've learned your thermal radiation laws. You've learned about the greenhouse effect. This is just an advanced form of it. This allows us to build our models. And what we want to do is we actually want to make sure that we're doing a good job with our models, that we're reproducing reality. So we can take our data. So here we have the change from the average. So we're tracking the change in temperature, the climatic change in temperature. And we can go ahead and look. The black is the actual data that we have measured. And then the color information are our models. And the way that we do the models is we have a whole bunch of models, and just like any good science where you have a whole bunch of measurements, whether they're model measurements or real measurements, then you take the average and then you look at the range of all the different ones to define an uncertainty. The lighter parts are the uncertainty, is what could have been measured. So now that we know what the data is, what our model does, we can incorporate the greenhouse gas forcing factor, and we can leave it out of our models. We can run both cases. We can also run time backwards to make sure that we're matching the data, that our model is doing a good job. And you can see from the past, just historic data, yeah, the model does a good job at matching the data. We have seen the most dramatic increase recently. And if we only do natural forcing factors, we don't include human-produced CO2 forcing factor, the model keeps a pretty steady thing that's going on, and you cannot match the data. You go ahead and you put the forcing factor from CO2, we match the data extraordinarily well. So another thing that is tossed around there that is just not true, the predictions of climate models, the scientific climate models, where you're actually looking at the models, the average and the uncertainties. If you actually go look at the IPCC reports and all the scientific papers, have been astoundingly correct in their predictions. So we use the CO2 information we get, we put in all the forcing factors, natural and from human-induced CO2. We run the models not just once, but a statistically large number of times, where we know what the errors of that we're putting into all the different factors we put. So we will go ahead and vary those and run them to see how that would play out. So we get the average, the average answer, and then we get the uncertainty, what we could have measured. That's the light shading again. And we can only match what we've seen if we put the CO2 factor in. And yes, this is a statistically significant result. And this recently passed a huge waypoint of that 5 sigma standard, where by chance the models would reproduce the data only once out of 3.5 million times. That is the gold standard in science. So we need the greenhouse gas forcing factor from CO2 to reproduce what we actually observe. Okay, so that's how we're sure that our models are working and actually giving good predictions. Now we can let these models run into the future. things that where we don't have data because we don't live in the future. And we can see what kind of changes we can expect with the appropriate uncertainties. So this is from the IPCC report number 4. 5 is already out, but they don't have a nice plot like this. 6 will be out in 2023 or 2022. So I just want to share how we actually go about understanding climate change as we project this into the future. We've already seen that it matches the data really well. We can reproduce the historic record by running our models backwards. And what we do is we run a variety of scenarios. So what we're going to do is take our models, which we've confirmed, we're going to extrapolate them. And what we're going to do is consider different scenarios. So this yellow one right here is if we stop all human produced CO2, if we stopped it in the year 2000. So stop using fossil fuels or have net zero CO2 added to the atmosphere starting in 2000. And this is the changes that we could see. And then we have a variety of other other ones where we phase out. I think this one, somewhere between the blue and the green, was supposed to be what the world is doing, but we're not really doing that. And then if we just continued unabated at our current output, that's the red worst case scenario. So notice that this goes out pretty far into the future. This is 2100. And it's giving you how much of a temperature change we should expect in degrees Celsius. And again, each one of these has error bars. Notice the error bars get larger the further out into the future you go. This one is another one, and it has a little bit more information. I'll let you digest this mostly on your own, but notice it goes out to, here's out to 2100, but this one goes all the way out to 2300, and we know that errors will grow larger, our uncertainty grows larger with time, so the error bars become pretty big out into the future. But this is just our projections right here, and you can see the error bars are not that bad here in the near future. So this is what we should expect based on all the physics that we now know and understand and very carefully account for. And what these different models are now, you see the RCP, that's representative concentration pathway, that's what scenario we're gonna run, and then the number is the increase in the forcing factor. So 2.6 is an increase of 2.6 watts per square meter. And then 4.5 is 4.5 watts per square meter, so on and so forth. And I'll let you digest that information on your own. I know this video has been long, but it is an important topic. If you have any questions about this, please go ahead and post them in the Canvas discussion, contact me via email, or attend one of the Zoom live sessions. All right, so that ends lecture module 3. Thank you for tuning in. Don't forget that the post-lecture engagement exercises are due this Friday at 11:59 p.m.